With a quick question.
Sure.
So I have an engineering resume. It's the format that, you know, school likes and all that.
Mhm.
And on it, I have previous work experience.
Okay.
My previous work experience isn't related to engineering. It's
Mhm.
like working as a fry cook, working as a lifeguard. Should I just delete that section, or should I still leave that there? Because, like, you know, it was from a few years ago, so now it's like applying as an engineering senior. I feel like putting, you know, a lifeguard from when I was a freshman in college kind of is not really related to the topic at hand.
I think it's still important because I mean, engineering is just like any other job. Like, you got to show up to work, you got to do what you're assigned to do, and so, you know, employers want to know that first and foremost, even before your technical skills. Because you could be the smartest guy in the world, but if you don't show up to work, then, you know, what good are you to the company? So
Okay.
showing that you had those jobs and you could hold them for a while is valuable for the companies. You know?
Okay. It's just like I have all these engineering projects, and it's like I was a lifeguard and a fry cook. It's just like it feels just like it's kind of a sharp contrast.
No, I think it's fine.
Okay.
I mean, I would probably spend. I think the thing that's probably most important for those jobs is, you know, the duration at which you held them, because that means you could hold a job for a while.
Yeah.
I would probably not elaborate too much on maybe your responsibilities, but maybe focus more.
I don't really do anything besides just like customer service and stuff, the basic stuff. All right, thank you. That's really all
I think just listing that is good.
Okay.
Yeah. Mhm.
I was, I got my internship opportunities this summer, so I don't know if I'm gonna go to it anymore. Oh, you're talking about like senior side projects and stuff? I think I'm still gonna go to it, just get ideas, possible suitable. But I got my internship opportunity, so I'm not really going there for that anymore.
All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. Welcome to our first in-person session for EGME 442. So it's exciting, nerve-wracking at the same time, but lots of emotions, but we'll deal with them, I guess. Okay, so the plan for today is we have a little bit of lecture notes to finish up from last time. Okay, and so we're going to finish that up today, and then we're going to start the next set of lecture notes, which is about medical imaging. Okay. And we might be able to do everything today because the medical imaging stuff probably is not going to take that long. And so if we do that, then on Thursday, we'll probably start something. Okay. I think that's all my announcements. And so are there any questions I can answer before we get started? Okay. All right, and so for those of you joining on Zoom, same policies we had before, so you can turn on your mic to ask questions or drop it in the chat, and I'll be happy to. Okay. The only thing the thing I don't like about this room is that it's kind of like freaking big, and so it's a little bit hard for if you guys are having trouble hearing the back, just let me know, and I'll just yell louder through my mask. Okay. All right, so let's go ahead and pick up where we left off because we kind of left off at a very I wanted to say kind of one more thing about Murray's Law before we left, but it was already over time. And so I thought I'd say it for today. And so we were going over Murray's Law last time. Okay. And the whole idea with Murray's Law is, we're talking about, or we're analyzing how a blood vessel will bifurcate, right? And so remember, when we say bifurcation, what we mean is that it's when a blood vessel comes in and then splits off into two paths, right? And so, if we call the radius of this vessel R1, we can call the radius of this vessel R2, this one R3, okay? Where this one right here is the parent vessel. And these are the daughter vessels, okay? Blood vessels are capable of, I guess you call asexual reproduction. So you can have just one parent and 2 kids. So that's a nice thing about that. All right. And so what we were interested in is, is there a relationship between the radii of the parent vessels and the daughter vessels? And what we derived at the end of class last time was that the relationship is governed by basically energy efficiency or power efficiency, right? Because we have such a vast network of blood vessels inside our body. Remember, we have literally thousands of miles of blood vessels in our body. It has to be an energy efficient system in order for your single heart to pump blood throughout the whole thing. Right? And what we said back there was that there's two main contributors to, or two main factors that cause that require energy for your heart to pump blood through. Okay. One was the viscous losses. Okay. Another way to think of the viscous losses is that, you know, as our vessel gets smaller, it takes more energy and more power to kind of squeeze the blood through those small vessels. Okay. Okay. The other competing factor has to do with inertia. Okay. And the whole idea with inertia is that as our as our vessels get bigger, it's going to take more energy and more power to push just a higher volume of blood through the body. Okay. Okay. Right. And so we have two competing factors, right? And so on the one hand, if we make the radius bigger, it's going to cause, you know, the inertia to go up, but the viscous forces go down. But as we make the radius smaller, it's going to make the viscous forces go up, but the inertia go down. And so, you know, whenever you know, this is not an uncommon situation in physics. And so whenever you have two competing factors like this, there's usually some kind of sweet spot in the middle of them that where it's most optimal. Okay. And so we went through the derivation last time, and so I'm not going to go through it again. Okay, but basically the upshot is that there's an optimal radius relationship where these two factors are minimized. Okay. And that relationship has to do with, you know, parent and daughter vessels. And so if we go back up to our diagram here, and we remember that R1 is the parent vessel radius. Okay. And we have R2 and R3. Okay. These are the daughter vessel radii. Okay. In order for this to be as energy efficient or as power efficient as possible, then the relationship is we have basically a cubic one. Okay. And so the relationship we have is that if we take the radii of the parent vessel and we raise it to the third power, that's going to be equal to the sum of the cubic powers of the daughter vessels. Okay. And so we have R1 cubed is equal to R2 cubed plus R3 cubed. Okay. And this relationship, the simple cubic relationship, is known as Murray's law. Okay. And so that's where we left off last time. And so the very last thing we did was we kind of arrived at this formula here. Okay. Are there any questions on this so far? Just this kind of summary from last time.
Yeah.
Yep.
So we spoke about
Plaque buildup. Yeah.
is that because there's like residue blood sitting there, or is it just because of the pressure?
Yeah, no, it's a great question, and it's something that's still being studied today. the exact mechanisms for, how plaque builds up. But kind of the discussion of that, I'll kind of save that for a later time, because it's we'll talk about that in detail, probably starting on Thursday, actually. Starting Thursday, and we'll carry it over into next week. Yeah.
My second follow-up was, 'cause if there was blood built up there, was that equation still true?
Right. No, it's a great observation, because this equation assumes that there's no plaque buildup, and so this is kind of a perfectly healthy kind of idealized system. And so once you start getting plaque builds up, then that changes the fluid mechanics of the vessel, and so that's going to modify this relationship. Yeah. Mhm. Okay. And so let's kind of recall our assumptions, that we made in getting this relationship, because we actually did make quite a bit. Okay. And so the main assumptions that we made were, first of all, that the flow was steady state, right? Because our Murray's law here was based on our solution to the Navier-Stokes equations, which, we can only solve that in the steady state. Okay. And our other main assumption was that we assumed that the walls were rigid. Okay. Or in other words, the walls of our vessel didn't move at all. Okay. I think we discussed it last time. Even though these are not necessarily true in the cardiovascular system, they are kind of reasonable assumptions to start with, but they aren't true. Okay. And so if you actually take some measurements inside a typical person, it'll be very hard to find blood vessels that follow this rule exactly. Okay. And so there are some deviations based on the vessels, and a lot of those deviations are due to how much the flow deviates from these assumptions. Okay. And so most cardiovascular flow And so let me give you some general, or some just general measurements that we have, or that we know, and we'll see how closely they deviate, or how closely they follow Murray's law. Okay. Even though it's hard to find vessels that exactly follow Murray's law, it does actually still provide a good starting point. Okay. So kind of a generalized Murray's law looks something like this. And so if we have a parent vessel R1. But instead of raising it to the third power, I'm raising it to just a general coefficient alpha. Okay. And so that alpha, the value of alpha, is going to change depending on where you are in your cardiovascular system. Okay. So I have a little table here that kind of shows you, how those deviations are occurring. Okay. And so I'm gonna give you kind of different classifications of blood vessels that we have in the body. I'll show you what their diameters are, and then also what their alpha value is. Okay. So let's start with the larger arteries. Okay. And so the larger arteries will have diameters anywhere in the range of 0.2 to 0.5 centimeters. Okay. So we call them large arteries, but their diameter can only get up to half a centimeter, and so you can see that all your blood vessels are really small, and so these tend to deviate from Murray's law the most. Okay, and so their alpha coefficient, or their Murray's law coefficient, ranges somewhere in the ballpark of 2.4 to 2.65. Okay. So now let's talk about some of the smaller arteries. And so these have much smaller sizes. Okay. So they're, bless you. So they're about an order of magnitude smaller. And so their diameters are about 0.025 centimeters to about 0.05 centimeters. So, getting pretty tiny, but we can still see them with the naked eye. Right? These tend to get a little bit closer to Murray's law. Okay. Okay. And so the Murray's law coefficients will be around 2.65 to 2.9, again, kind of loosely based on the size. And so the next classification of blood vessels that we have are called arterioles. And so these are, I'm not sure if we talked about these yet, but these are basically the vessels that lead up right up until the capillaries. And so these are kind of like the transitional vessels as you go from like some of the larger arteries down to the smallest capillaries. And so, these are getting to be among the smallest ones. And their sizes are anywhere on the order of 0.005 centimeters to 0.025 centimeters. So, so quite a big range here. Okay. And their Murray's law coefficients will be anywhere in the ballpark of 2.75 to around 3. Okay. Right, and then the smallest blood vessels you have in your body are, of course, the capillaries. Okay, and so those have diameters, less than 5 microns, basically. And these are really the only blood vessels that follow Murray's law to a T. Okay, but for most other blood vessels, you have some deviation from Murray's law, but they still have this this kind of relationship right here. Question? Yeah.
When you age, like your body like develops a good teenager, do your arteries ever like grow in diameter, or are they pretty much the same magnitude?
So they actually the reverse happens, and so they actually tend to get a little bit smaller, because as you age, you have certain materials in your body called collagen and elastin, and so as you age, and those are properties that give your blood vessels flexibility. And so as you age, you tend to lose those, or they kind of, they don't have the same properties as they did before. And so as your blood vessels get more stiff, they tend to kind of constrict up. Like that.
That happens at a young age.
Wait a second.
Your vessels get stiffer at a young age as well.
It's possible. It is possible to get stiffer at a young age, but and those are usually due to some kind of disease or some kind of pathological condition. But as people get older, then that's kind of just a natural part of aging, is that their blood vessels get stiffer.
One last thing. Problem 3 for homework.
Yeah.
It asks if Geiger's supposed to true or false.
Mhm.
Would it be false because you can't use Geiger's supposed for like the bigger capillaries? Or
Mhm.
would it be true since you can't use it for the smaller capillaries?
I'd say you have the right idea. I'll let you go from there, but I'll let you rest. Part of that question was having you guys wrestle with that logic, because you have both sides of the argument, and I want you to decide which one is the way you should go for that problem.
I forgot we're all there, a bunch of people on that. So.
Wait, what? Wait, say again.
What?
Wait, say again.
I said I forgot we're all there, a bunch of people on that. So.
Okay, I see. There's a question here too.
Didn't you say that the capillaries tend to fail with Navier Stokes because they're non-Newtonian, the blood flow?
Yep.
But then they work for Murray's law, so it's like.
So that's a good point. So so remember, Navier-Stokes assumes that we have the the relationship between shear stress and strain rate is linear, right? And so you're right. So the fluid velocities don't necessarily follow in the capillaries, because you have the blood cells, but their measurable size of the blood vessels follow Murray's law. So Murray's law is just a statement of how the different sizes of the blood vessels link to the pairs. Yeah. We derived it using Navier-Stokes, but that relationship still holds down there as well. Yeah. Mhm. Okay. Great question, by the way, guys. And so, the main reason we see deviations for the larger vessels is because they don't follow these assumptions as well. Okay? Or I should say, the larger the vessels are, then the less they follow those assumptions. Okay. And so a larger vessel will typically be a lot more flexible because they have a lot more collagen, a lot more elastin. And their flow characteristics are very unsteady. And so, the larger the vessel is, they tend to be closer to the heart. And so the closer the vessel is to the heart, the more kind of rapid oscillations you'll see. And so that's why for, the bigger arteries, you have a much larger deviation from those. Okay. Any questions on it? Any other questions on this so far, before we move on? Okay. Okay. Sometimes I forget to check the chat. Okay. All right. And so I want to bring your attention to one more thing. Okay. And that has to do with with this radius relationship right here. Okay. All right. So one thing I want you to notice that even for the larger arteries where the deviation is the highest, the exponent is still greater than 2. Okay. And why is 2 significant? And so an exponent of 2 corresponds to area, right? Okay. And so in other words, if we were to say that our blood vessels are area conserving, then we would have a relationship like this, right? Okay. And so if the sum of the 2 daughter areas are equal to the parent area, then what we say is the bifurcation is area conserving. Okay. And if we plug in if we assume that all the blood vessels have a circular cross section, and so we have pi r1 squared is equal to pi r2 squared plus pi r3 squared. Okay. And you can see here that we have pi's all cancel out. Okay. Then if the bifurcation were area conserving, we would have this relationship right here. Okay. But what we have is not the case, right? And so all of our exponents are greater than 2. And so what this means is that the total cross-sectional area, every time a blood vessel bifurcates, you can think of like the total cross-sectional area of all the blood vessels in total is going up. Okay. And that's another essential feature of our arterial system as well. And so we'll come back to that once we talk about arterial biomechanics. Okay. And so now that we've covered Murray's law, the next thing I want to go over in this set of lecture notes is the wall shear stress. Okay. All right, so the wall shear stress is a very important quantity, and it's going to be a very important concept for your final project as well, because this is one thing that simulations can do really well, that normally it's really hard to measure this inside the body. Okay, so let's define it first. Okay? So the wall shear stress is the viscous shear stress that the fluid imparts onto the vessel wall. Okay? And so in other words, that's kind of a fancy way to say that, you know, whenever a fluid flows past something, there's going to be some frictional force that the fluid imparts onto the solid, right? And so the wall shear stress is basically an expression for that frictional force. Okay? Okay. And so for the vessels that we're considering, where, you know, we assume that the blood vessels are a tube or a cylinder, this means that we're going to evaluate the shear stress at the vessel radius. Okay. Okay. And so let's write out the expression for the shear stress. Okay. And so we're going to be assuming we have a Newtonian fluid. Okay. And so for a Newtonian fluid, the shear stress is equal to mu, which is the viscosity, multiplied by the derivative of the velocity. And so this should be du dr. Okay. Right. And so to make sure that this is the wall shear stress, we're going to evaluate this velocity derivative at the vessel wall. And so so basically we're going to plug in little r is equal to big R. Okay. So just to make this a little bit more clear, let me do this. Okay. Because we have an expression for UZ of R. That's what we found when we solved Navier-Stokes. Okay. And so all we need to do is just plug in for UZ of R in this case. Okay, so let me go ahead and do that. Okay. And so if we plug in our Navier-Stokes solution, we have mu times DDR times 1 over 4 mu. 1 over 4 mu times the pressure gradient dP dz times r squared minus big R squared. Okay. Right, and so we take the derivative of this. We know that big R here is a constant, and so when we take the derivative, it's just going to go away. Right, then we're going to take the derivative of R squared, which is just going to be 2R. Okay, and so we do that. We have mu times 1 over 4 mu dP dz multiplied by 2R. We have the mu's here that's going to cancel out. We have this 2 here that's going to cancel out with the denominator, and so that's going to be 1/2. Okay. And then we're evaluating this, or in other words, we're plugging in little r is equal to big R here, okay? And so our expression for the wall shear stress is equal to simply big R divided by 2 multiplied by dP dz, okay? Right? And so we end up with a fairly simple expression in terms of the pressure gradient. Okay? And so we just take the pressure gradient, we multiply by the radius of the vessel, and then we divide by 2, and that gives us our wall shear stress. Okay. Right. And so this expression right here, even though it's simple, a lot of times it's not that useful for us for calculations because the pressure gradient oftentimes is a little bit hard to measure. It's a little bit hard to determine. And so to make this equation a little bit more useful, let's plug in for the pressure gradient and put it and make it in terms of flow. Okay. And so remember, our symbol for Q, or our symbol for flow was Q. Okay. And in last class, when we saw the Navier-Stokes equation, we saw that our Q was equal to minus pi r to the 4th divided by 8 mu times dP dz. Okay. And so if we kind of solve this expression for dP dz, and so we move this over to the other side, okay, then we get dP dz is equal to minus 8 mu q divided by pi r squared, or excuse me, pi r to the 4th. Okay. Okay. And so now that we have that that expression for the dP dz, we can go ahead and plug this in to our wall shear stress formula. Okay. And so if we do that, we get tau W is equal to minus 4 mu q divided by pi r cubed. Okay. Because the divide by 2 is going to change this 8 to a 4. And we're also losing a power of r because r is going to cancel out with the one on the bottom. Okay. Traditionally, the way that this is expressed here is we just ignore the negative because a lot of times we're interested in just the wall shear stress magnitude, and so the negative there expresses some form of direction. Okay, it's to basically express the fact that wall shear stress kind of goes one way, but most times we're just interested in magnitude. Okay? And so when we take the magnitude, then we get our probably the more useful expression for wall shear stress, which is 4q mu divided by pi r cubed. And this is what's known as the Poiseuille wall shear stress formula. Okay. I always forget how to spell his name, so I'm going to go ahead and look it up. And so in other words, if you can assume that we have purely parabolic flow in a cylindrical vessel, in other words, you have a Poiseuille flow type of solution, then this is an expression for the wall shear stress. Okay. Any questions on this? So this formula right here is actually, even though it looks pretty simple, it's actually useful just for getting an expression for wall shear stress, because normally, if we can kind of think back practically for a minute, measuring the wall shear stress is normally extremely difficult. Even in laboratory setups, it's hard to do it just because it's such a fine thing. Right? Because if you have a blood vessel, right, and you have blood that's flowing through the blood vessel, okay, and in fact, let's make this accurate. Okay, so let's make it a parabolic flow. Okay, the wall shear stress is basically, what we're measuring is the amount of viscous forces that's occurring right here. Okay, so this right here is the wall shear stress. And so normally, even if you have very, very well-tuned laboratory equipment, this can be hard because, quantifying that force when the blood is kind of moving so quickly by you or any kind of fluid is normally pretty difficult. And so to have a formula like this where, you take something like flow rate, which is, very easily, or not easily, but a lot more easily measured, right? And so that flow rate is just an expression for how much the volume of blood that gets pushed through a vessel in an instance of time. Okay, it depends on the radius, which is measurable, and so to have a formula that can take those two quantities that are relatively measurable and compute something that is normally very hard to measure is really useful. Okay, even for blood vessels that don't necessarily follow the Murray's law exactly, or don't necessarily follow the assumptions that we made, this can actually give you a good approximation. And and a lot of doctors actually use a formula like this to to kind of make like an offhand guess on certain things. You'd be really surprised actually, and we'll talk about this when we get to medical imaging. You'd be very surprised at how many kind of how much doctors really love these kind of, the way they see is kind of like relatively simple engineering formulas, just to kind of help them with their work. Another one that they really like in blood flow is Bernoulli's equation. So do you guys remember Bernoulli's equation from fluids? And so if you remember Bernoulli's, it has a ton of assumptions that you have to make in order to make it valid. But what doctors do, they just said, we're just going to pretend that those don't exist. And so they apply Bernoulli equation in quite literally probably the worst possible cases that you can do it. But they still use that Bernoulli equation to give medical diagnoses, which is kind of a scary thought. But they make it work somehow. And I'm not saying I'm not throwing shade at them. I'm just saying it's interesting how they can make those things useful. I'll leave it at that. Okay. And so the last thing I want to talk about before we move on to medical imaging is I want to take this result for the wall shear stress and combine it with Murray's law. Okay. Okay. All right. And so remember, Murray's law was an expression of how the radii change when you're coming to a bifurcation, right? And so in its purest form, Murray's law was R1 cubed is equal to R2 cubed plus R3 cubed. Okay. Where remember, on one side, this is the parent vessel. And here we have the daughter vessels. Okay. Let's make an additional assumption on this, just because it kind of makes the math a bit easier. And let's assume that both daughter vessels are the same size. Okay. Okay. And so if both daughter vessels are the same size, then we basically have R2 is equal to R3, right? And so our Murray's law expression is then going to be, I'm just going to use R2. Actually, let me do this. And so let me call the parent vessel artery, we'll call it RP. And the daughter vessel, we'll call it RD, okay? So, this is not always true. But just for this derivation, I'm just going to make this assumption, just because it makes the math just a whole lot easier. Okay. Another thing that we're going to say is that we're going to enforce conservation of mass. Okay. Remember, conservation of mass states that the flow rate that comes into a bifurcation is going to equal the flow rate that goes out. Okay, and so if we express that mathematically, we can say that Q of the parent vessel, this is going to be equal to the sum of the Q's of the daughters. But if both the daughters are the same size, then we have this relationship right here. Okay, and so we're QP here. This is the flow into parent vessel. And this QD right here is flow into daughters. Okay. All right, and so we have these two relationships that are born, born from Murray's law. Okay. So let's take these relationships and use them to evaluate the wall shear stress in the parent and daughter vessels. Okay. Okay. All right, so let's start with the parent first. Okay. All right, and so for the parent, I'm just going to use the formula that we have up here. Okay. And so the wall shear stress in the parent vessel is going to be 4 times QP, which is the flow rate in the parent vessel, multiplied by mu, all divided by pi RP cubed. Okay. And so if we do the same thing for the daughter vessel, we have tau W is equal to 4 times QD mu divided by pi RD cubed. Okay. Okay. Let me make this D a little bit smaller to make sure that it's a subscript. Okay. All right, so you can do this either way, but I'm gonna do it from the parent side. Okay, and so I'm gonna substitute directly in for QP and RP. Okay, or specifically RP cubed, because through our Murray's law and through our conservation of mass, we have these expressions for QP and RP. Okay, and so we plug those in, and so QP from our conservation of mass is equal to 2 times QD. Okay. Times mu. This is divided by pi. And instead of RP cubed, through the Murray's law, we have RP cubed is equal to 2 times RD cubed. Okay. Right. And so, of course, we have a 2 in the numerator, a 2 in the denominator, and so those are going to cancel out. Okay. And so if we write out the final expression, okay, we have the wall shear stress in the parent vessel is equal to this. Okay. And what you should notice is that the expression that we get for the wall shear stress in the parent vessel is exactly the same as the wall shear stress in the daughter vessel. Okay. It's like magic, except it's math, so it's mathic. All right. Any questions on this? And just how we got this result? Yeah.
It's not so much about the actual getting the results. So does this mean that for most of our blood flow in our body, with all the bifurcations in our system and all that, our bloodstream all feels the same shear stress?
Basically, yep.
Okay.
Mhm, yep. And I'll explain why in a second. It is that's definitely the result, but it's that way for a good reason.
Okay.
Yeah. Mhm. All right. So like Hutton just mentioned, what this means is that the parent and daughter vessels feel the exact same shear stress, and so as you go through your blood your blood vessel tree, and so I'm going to draw kind of a very small approximation of that. Okay. Right. And so your blood vessels in your body are a very complex set of branching vessels. Okay. And so if this result is what this result is telling us is that every time we bifurcate, we still feel the same wall shear stress, no matter what. Okay. And so for if we can assume that the Murray's law and conservation of mass hold all throughout the cardiovascular tree, that means every single blood vessel will feel the exact same wall shear stress. Okay. And there's a very good reason for this. And so, one of the important I guess differences between your blood vessels and maybe like a pipe that you would find under your sink is that the blood vessels in your body, the walls are lined with cells, right? Remember we talked about this in our kind of our anatomy and physiology part, right? And so these cells, their kind of broad name is known as endothelial cells. And these cells are the same, no matter for your biggest blood vessels or the smallest blood vessels, okay? Okay. And so since these cells are lining the inside of your blood vessel wall, they're going to be the ones that actually feel the brunt of the wall shear stress, okay? Okay. And so it makes sense that, if you have the same cells on the inside of your blood vessel wall, for your biggest vessels and the smallest ones, it makes sense that they would want to feel kind of the same kind of dynamic environment that that all their peers would have, okay? And so this result that, the wall shear stress is relatively the same throughout your whole body is mostly a result of keeping these endothelial cells happy. Okay? And this desire for those cells to maintain the same kind of dynamic environment or same kind of force environment, it's not that they're picky or anything. It's not that they only like one flavor of wall shear stress. It's more a function of for a lot of biological beings, and of course you're no exception, and the endothelial cells are no exception. There's always going to be a complex cascade of like chemical and biological reactions happening in your body. And a lot of those reactions are triggered by things like forces, things like temperature, things like hormones and stuff like that. Okay. And so in order for your blood vessels to kind of maintain proper shape and to make sure your entire body's kind of functioning biologically like it should, you know, it wants to kind of, you know, your body wants to kind of maintain the same kind of mechanical stimuli in it so that, you know, all the processes can happen as they should. Okay. And so that's kind of the reason why, you know, your blood vessel tree tries to maintain that same wall shear stress. Okay? And this kind of phenomenon and this kind of desire to kind of maintain the same kind of you know, state, same kind of stress, same kind of temperature, is known as homeostasis. And so stasis, you know, is a kind of a word for staying still or keeping the same conditions, and homeo stands for, you know, human body, basically. Okay, and so that's kind of the origin of those words. But there's a big if in this, right? And so, you know, in reality, you know, if you measure the wall shear stress inside, you know, a real person, you're not going to get the same value of wall shear stress, and so there's no magical wall shear stress that's happening every time in your body, because there's a lot of factors that can influence it. And, you know, just naively, you know, the big if that we have here is that if Murray's law holds. Right? We've already seen that, you know, for a lot of blood vessels, you know, depending on how big they are and how much they deviate from rigid steady flow, you know, Murray's law might not hold perfectly for all those vessels. Okay? And so, you know, when you run your simulations, you know, later on for your project, you know, you're not going to get the same wall shear stress throughout the whole system. If you do, you probably messed up somewhere. And, you know, we probably should talk, but you know, it's not going to be exactly the same, but they do. And so the way that homeostasis is usually defined is that there's usually a range of wall shear stresses that your body is comfortable with. Okay, and so as long as your body kind of maintains within that range, then it's going to be happy for most of the time. And there's other things that can happen too. So, you know, like you can see me, I'm like waving my arms around, and of course, you know, as I wave my arms around, it's going to affect the blood flow in my arm as well, right? And so you can kind of cut off the circulation in your hand. And so, you know, it's not a life or death thing where, like, if you have to maintain your wall shear stress, otherwise you're going to die. You know, there's some flexibility in the system, but, you know, the long-term average, or, you know, over time, they want to kind of maintain that range. And of course, you know, if you have disease as well, then that's going to affect the wall shear stress values too. Any questions on this before we move on to medical imaging? Okay, all right, and so that's the you know, that's our discussion of steady flow and rigid vessels. And so we kind of started this lecture notes with just a review of fluids, but you can see that, you know, even with kind of elementary fluid mechanics of just doing Navier-Stokes in a rigid vessel, you know, we can still come up with a lot of really interesting conclusions and a lot of really interesting biological you know, effects as well. Now I want to shift gears a little bit, and so I want to talk about the technology a little bit. So let me go ahead and share my laptop, my computer screen here. Okay. I should have prepared this before. Okay. Because the first thing that we're going to do, of course, I'm logging in. The first thing we're going to do next week is we're going to do our first tutorial in SimVascular, and so, you know, before we talk about SimVascular, I want to make sure we talk about things like CT scans, things like MRIs, just so that you know what they're supposed to be or how they work. Whoa, send me push requests. Oh. The system wants to end lecture early. See this. Sorry about this, folks. There we go. Okay. Fourth time's the charm. Okay, all right, we're back. Sorry about that. Okay, so I want to talk about medical imaging. Okay, ignore the date. It's spring 2022, but I just haven't changed it since the last year. Okay. Okay. So what is medical imaging? And so, when we talk about medical imaging, I think most people kind of have like an intuitive feel for what that really means. And so you probably imagine something like you see on the right here, where you have a person visiting the doctor and they're getting some kind of scan. They're going through some machine, or you've probably seen an ultrasound machine where doctors kind of determine the determine if you're pregnant, or determine the sex of the baby, right? And so medical imaging is a very broad term. And so what it refers to is just any use of medical diagnostic equipment to obtain visual information about a patient's anatomy and physiology. Okay. And so the key here is, visual. Okay. And so there's a lot of diagnostics that you can take on a person, but whenever you get kind of any kind of visual diagnostic inside a person's body, that constitutes medical imaging. Right? And so some examples that you may be familiar with are things like X-rays, things like MRI, things like ultrasound. Okay, so we're going to talk about all of those today. And the reason we do medical imaging is to, obtain useful information from a patient that normally you wouldn't be able to see from the outside, right? And so this information can be used to assess the health of the patient. It can be used to diagnose disease, or or for a lot of cases, it can be used for research as well. Okay. And so today, what we're going to do is we're going to today, and probably a little bit on Thursday too, we're going to briefly cover all the different types of imaging. We're going to explain how they work. So we're going to explain their physics, and so I think that will be kind of interesting. And we're going to discuss some applications. Okay. The field of medical imaging is very vast, and so we're just mostly going to focus on the ones that apply to the cardiovascular system. Okay. And so the reason I want to talk about this right now is that when we do our first vascular tutorial next week, you're going to be getting the medical image data of a patient. And so it's going to be the CT scan of someone that got their chest scan, and you're going to be building basically a CAD model of the person's blood vessels based on their medical imaging. So, I thought that, since you're going to be working directly with medical imaging, it'd be good to kind of talk about, what it is, just so you can have, a little bit of appreciation for, what went through to get this data set. Any questions on this so far? Okay. All right, so let's talk about some of the types of medical imaging. So there's a couple. And so the one I think people are mostly familiar with is called structural imaging. Okay. And so structural imaging refers to techniques that provide information on geometry and motion. Okay, so basically just the structure of the inside of your body. Okay. And so structural imaging is nice because it allows for visualization of organ shapes, volumes, and also blood flow patterns and speeds. Okay. And so the most common types of structural imaging are things like X-rays and MRI. Right. So you get an X-ray, you get an image for what your bones look like, or for what your teeth look like. You get an MRI, you can get images of soft tissue. Okay. The other type of imaging that's kind of still being researched, and I think it's kind of a really hot topic right now, is known as functional imaging. Right? And so functional imaging, in addition to providing some information on the structure and geometry, it can also give you information on physiological function. And so things like blood perfusion, or that's an important metric for doctors to see, how well does your blood saturate a certain area, right? And so normally you would want to have high blood perfusion, just to make sure that your muscles and all your organs and all the tissue in your body is properly getting all the nutrients and oxygen that it needs. Okay? As well as some other chemical and biological function. And so one kind of input for functional imaging is the injection of what's known as a contrast agent. Right? And this is true for structural imaging as well, because there's just some things in your body that are really hard to pick up on imaging. And so to kind of help with that, something like a fluid is injected into your body to make it show up more brightly on the image. Okay. And we'll talk about some of the ones that are used for your blood, which is what we're going to be talking about a lot. But also, for a lot of imaging that's done in your gastrointestinal system, and so through your intestines, or through your stomach, or through your esophagus, sometimes the sometimes doctors will have a patient, swallow a pill or something, and that's going to basically light up your intestines on an X-ray. Okay.
Good question.
Yeah.
Going going back to the structure.
Mhm.
How would that work? It's just a snapshot. Like, how would you be able to get?
Yeah. There's different kinds of structural imaging, and so there's definitely static imaging where you just get a single snapshot. But there's a lot of techniques nowadays where you can actually get a video of a person's blood on the inside. And so one of the more popular ones is called 4D MRI. And so for the fourth dimension is time, that's what they call it. And so they basically take a continuous MRI inside your body so that you can get like a small video or a small animation of what the blood pattern looks like on the inside. So yeah, exactly. Yeah. So they basically just take a bunch of images, sequenced after each other, and then you just kind of view them very quickly to see what they look like. Yeah, it's pretty cool actually. All right, so let's start with the simplest imaging that there is out there, called known as X-rays. And so hopefully everyone's got an X-ray at some point in their life. And the technology for X-rays actually goes back all the way back to the 1800s. And so it's a very, very old, very mature technology. Okay. And so basically how they work is that X-rays, which are basically a form of radiation, they're produced in a device called an X-ray tube, and then they're basically shot through a patient, right? So basically just like as you see on this image on the right. Okay. And so as the X-rays pass through the patient, they're collected on another device called a detector, okay, which is going to basically give you your snapshot inside the person's body. Okay? And the reason that this works is that as you pass the radiation through a patient, then the different structures inside the patient, like things like bones, things like tissue, will attenuate, or in other words, deflect or otherwise slow down the X-rays as it passes through. And so what you can do is that you can say that, okay, let me measure, the intensity of the X-rays that pass through here, and the areas where the intensity is lower, that's where that's where your tissues and organs are. And so to get this image of the hands, right? And so if you can kind of look at your hands just like this, right? The way that this image was produced was, someone laid their hands out onto basically an X-ray detector, and they shot an X-rays through it, and the really dark black parts of this image, those are X-rays that kind of pass through unimpeded, and so those went straight from the X-ray tube to the detector, and so those are kind of, you can think of them as like maximum intensity X-rays, okay, and so that's why they appear really dark. But the X-rays that actually pass through your hand, those, your bone kind of attenuate those X-rays, so they kind of deflect it in a certain direction, or some of it gets absorbed, or some of it gets, otherwise, pushed aside, right? And so the parts that actually appear white are, the parts where, not as many X-rays pass through those parts, okay? And that's why, you're able to get this, really beautiful image of a person's hand, is because, because of that X-ray technology. Okay? And so certain materials that that do really well in attenuating X-rays are things like calcium, right? And so, of course, your bones are full of calcium, and so that's why you can see them really well in the X-ray. Okay. Your teeth are full of calcium as well, and so probably if you go to the dentist, they'll take an X-ray of your mouth. Okay. And one thing I didn't mention here too is that if you actually have very advanced cardiovascular disease, and so you have a lot of plaque buildup in your body, one of the responses that your body actually does to that is they actually produce calcium. And so what happens, and this is very late stage, cardiovascular disease, and you definitely don't want to be there. But when your plaque kind of starts to harden up in your body, that process of hardening is your body actually depositing calcium into those places. So you can actually see some blood vessels in just a regular old X-ray, because they start to calcify quite a bit, which is usually bad because you don't want to be in that area. But that's what tends to happen to some people. All right, and so soft tissue, so things like your blood vessels, things like your muscles, those don't really have that much of an effect on X-ray beams, and so you don't really see that much muscle or fat in an X-ray, right? And so you can see that most of the skin and most of the tissue here is mostly passed through. You have a little bit of stuff here, but it's not nearly as bright as the bones. Okay? And just like I mentioned on the previous slide, if you want to enhance certain areas that normally wouldn't be picked up by an X-ray, you can inject a contrast agent. And so if you want to have your blood vessels show up in an X-ray, then you can inject something like iodine into your blood. Okay. Or you can take a barium pill, for your gastrointestinal, and then that barium will kind of disperse. You can take an image of a person's intestines, and you can get an image like that of their intestines.
For the iodine, like, is there a limit to how much it shows? Like, if you inject, let's say, a bit of iodine in your arm, would it only go up like a certain part of your arm, or would you be able to actually be able to see your entire blood flow by just injecting enough iodine with no side effects?
Oh yeah, I mean it actually, it's surprising. It actually flushes through really well. And I've seen some real-time images of someone taking kind of a real kind of a live X-ray of a person's like beating heart, and they inject the contrast agent, and you can actually see it flush through all the blood vessels in the heart kind of in real time. And it doesn't persist for that long, but it'll persist for a good 1 or 2, 3 seconds, and that's usually enough time to get some good images there. And so your blood's actually moving really quickly. So you inject a little bit, and it disperses out really quickly. All right. Any other questions on this? Okay. And so the next type of imaging I want to talk about is the CT scan. And so the ones that we're actually going to use in Symbascular are CTs. And so CTs stand for computed tomography. Okay. And so even though it has a very different name, at its core, it's actually the exact same thing as an X-ray. And so the thing that makes computed tomography unique is that you take a CT scan always in a machine that looks like this. Okay. And what you don't see is that inside this tube, you actually have like an X-ray tube. Okay. And so that X-ray tube is going to be, spitting out X-rays throughout your body. Okay. But then what it does is that it actually rotates around the donut. Okay. And so the way it works is that it's basically an X-ray that's on a motor. Okay. And so the CT is going to rotate the X-ray tube really quickly, and throughout that entire time, it's going to be shooting out X-rays kind of all around your body, and it's going to be picked up by a detector back here. Okay. Which is also spinning along with the tube. Okay. And so by taking a ton of different X-rays at a ton of different angles, and of course the machine knows at what angle is taking it with as it's going around, that you can kind of reconstruct an actual like 3-dimensional image data set of a person's insides. Okay. And so this kind of overcomes one of the big weaknesses of the X-ray, which is you only get kind of a two-dimensional view. With this, you can actually get like a 3-dimensional view of a person's body, right? And a 3-dimensional view of their blood vessels on the inside. And the technique that the CT scan actually uses to create these images is known as back projection. Okay. And so the way, we won't get into the technical details of back projection because that's kind of like 2 full lectures on its own. But you kind of get the idea. Where you take kind of X-rays in a circle around a patient, and you kind of reconstruct the images from there. Okay. And so kind of the format for the data files for a CT scan, and you'll see this in Symbascular when we do the tutorial, is that it kind of displays your volumetric image as like a stack of X-ray slices. Okay. So it's almost as if you took, just like a few hundred X-rays kind of at different kind of cross sections in your body, and they just stack those papers on top of each other. Okay. And so you'll see that in Symbascular, the way that we view this medical image is, we can say that go to slice 50, and it's going to show you a certain cross section. Okay. But then if you move up, so give me slice 100, it's going to move up higher in your body as well. Okay. And so this idea of kind of viewing a 3D images as a bunch of slices is kind of good intuition to have for that. Question?
Yeah, isn't the X-ray not that good for your body? Can it take this much at one time?
That's a great point. And so the question is about radiation, right? And so it's definitely a very hot topic in the medical profession. And so when you do a CT scan, they are very careful with the amount of radiation because they know that they're taking a lot of images at the same time. And so they cut back the radiation dosage so that it's not harm to your body. And so it's very interesting because if you talk to people who do research in CT, they're like the raw CT people. They're like, we haven't had an issue in 25 years with radiation, and it's totally safe. But then if you talk
5 years ago,
yeah, that was just a random number. But then if you talk to the MRI people, they're like, any radiation is bad, you know, you're putting your patient at risk, and the image quality isn't as good as MRI. And so like people literally like, you know, they're at each other's throats, and it's fun being a fly in the room in those kind of arguments. I've been in several of them. Question.
That X-ray machine that rotates around you, it pivots around your body at the center of that rotation.
Yeah. Mhm.
So that means every picture is a different angle, not going to be parallel.
Correct. Yep.
So how do you lay all the pictures not connected to each other?
Yeah, so the process that does that is the back projection. And so, you know, it takes basically all those images and they kind of like put them on top of each other. And then it goes through a lot of kind of processing in a computer to kind of display it as slices, because the slices is kind of the most convenient way to view them as a user. But that's what back projection does basically, is it takes all those different angles and puts them into a nice kind of ordered
Are
stack.
they actually stacked flat on top of each other, or is it more like pizza pie?
They're stacked on top of each other, and so you know, or at least the way that it's displayed. So there's a lot of kind of engineering and kind of a lot of computer algorithms that kind of go under the hood. Yeah. Question. All right, question. So is it possible to create a 3D model from these back projections, a 3D model that you can navigate and rotate and views around a CAD program? That's a great question, actually. So one of my, it was actually kind of a side project that I was doing that I had in grad school. Was based on that actually, and so I didn't get to finish it because it was kind of at the tail end, but that's definitely something that people are interested in. And so, you know, especially if you have kind of a really high quality image. So there's another technique, we won't talk about it too much in this class, called angiograms. And so angiograms, they actually take images from not something like this where you have, you know, a million different angles, but you have, you know, 3 distinct angles, but the image quality is like really crisp, it's really good. And so I was looking into a method of kind of turning those 3 angles and maybe turning it into a 3D CAD model that we can use for analysis. But I didn't get too far, and no one really picked it up after me. Yeah. But there is some interest in that, and I'm not just saying that because I worked on it, but you know, people are actually interested. I swear they're interested in it. That's why I did. Okay. CTs, yes. Right. So CT scans. You know, the nice thing about CTs is that, you know, the machines themselves are usually relatively cheaper than MRI machines. MRI machines will usually run you up into the millions, but CT scanners are usually a few $100,000, you know, which is still a lot of money, but, you know, hospitals also make a lot of money too. So, and so you'll see CT scanners, you know, they're a little bit more common than MRI machines just because the financial cost is lower, despite the radiation component. But, yeah. All right, any other questions on CTs? Okay. All right, and so the next type of imaging that we'll go over is MRI. I think this will be the last one we go over today, okay? And so MRIs are, you know, you've probably heard MRI mentioned probably on ESPN or something, like someone sprained his ankle and they got an MRI. And so the nice thing about MRIs is that it allows you to image soft tissues a lot more easily than X-rays or CTs, okay? Because if you want to image, like, you know, cartilage or muscles with CT, it's normally pretty difficult because you have to inject something in order for it to register on an X-ray. But an MRI works, you know, from a totally different angle, and so it doesn't really have that weakness. And so whenever you hear someone, you know, sprain their ankle or something like that, or they have muscle damage, you know, most of the time they're going to get an MRI because it's a lot easier to get images of that exact muscle. Okay. And the way MRI works is it's really crazy. And so, you know, I kind of did my best to kind of explain it on one slide right here, but honestly, like, you read a book on MRIs and it's like you're meeting Jesus. And so it's like how the hell did someone even come up with this? And, you know, it's crazy. And so, you know, I think, you know, I'll give you the full explanation next time. But the whole idea with MRIs is that you know, it actually goes down to the atomic level inside your body, which is very rare. And so, you know, even techniques that go down to the cellular level are kind of crazy. But if you can come up with a technique that actually manipulates the atoms at the atomic level, it's pretty insane. And so the idea is that, you know, whenever you have an atom, you know, it has a certain number of protons or neutrons, okay? And you have an electron, electrons that kind of float on the outside. And so the whole idea is that when you have atoms that have an odd number of protons or neutrons, they actually have a very tiny magnetic pull of their own because they're kind of, have an odd number of protons. Okay. And there's a very particular atom that has an odd number of protons that make up a huge volume of a person's body, and that's hydrogen. Right? And so because a lot of our body composition is water, hydrogen makes up a huge portion of our human mass. And so the idea with MRIs is, can we use magnetic fields to kind of manipulate the spin on these hydrogen atoms inside a person's body, and then sequence that along with some kind of radio frequency in order to produce some kind of imaging. And so I'll leave it at that for now. And so on Thursday, we'll pick it up from here just because we are just about out of time. Okay. And so any final questions on this before we wrap it up for today? Yeah.
What specific conditions do MRIs help detect that if they're only like seeing the hydrogen? Like,
and so because
obviously there's a limited amount of things that they can view.
So most of the things in your body are actually made up of hydrogen. So like your muscles and your bones and stuff, there is still a fair amount of hydrogen in there. And so the MRIs are basically manipulating all the hydrogen in these tissues to produce images for you, like
Okay.
it's crazy.
It's crazy.
It's honestly crazy.
Magnets have
Yeah.
different,
All right, thank you, everybody. So I'll stick around for a little bit if you have any more questions, but if not, I'll see you on Thursday. So have a great afternoon, everybody.
Yeah.
No problem. See you guys. What's up?
Ultrasound athletes only, or is it part of?
Oh yeah, we'll talk about it. I think it's the very next slide. Actually. Yeah, ultrasound's the next slide. So we'll talk about ultrasound on Thursday. Yeah.
Everything that